This is AP Calculus BC, and in this video I'm going to talk about section 9.6. The primary focus of this section is alternating series, but we're also briefly going to discuss absolute and conditional convergence. So this is actually the last series test that we have, and this is one of the easiest for us to use. When we talk about an alternating series, what we're talking about is a series where the terms are going back and forth between negative and positive. And you can recognize alternating series pretty easily whenever you see expressions that have like a negative to the n power or a negative to the n minus 1 power or a negative to the n plus 1 power. Those are all going to be situations where you have an alternating series. Sometimes it won't be a negative 1. Like for example, in a geometric series, you might have an r value that's negative. That's not necessarily a 1. And it's still alternating. As you change the term number, it's going to switch back and forth between positive and negative. Okay, so let's take a look at two series that are very similar. So we've got the harmonic series, which remember we've looked at this before. It's 1 plus 1/2 plus 1/3 plus 1/4 and so on. And we know that that is a series that diverges. And we've talked about that one several times now. So primarily the p-series test would tell me that that one diverges. Well, if we look at the alternating harmonic series, so take a look at this one below here. What we have is, it starts out the same way. When I plug in n as 1, I get essentially 1 over n, which gives me a positive value of 1. When I plug in n as 2, now I have negative 1 raised to the 1 power, so it becomes a negative 1/2 here. And then it'll switch back to positive, and then back to negative, and so on, until I get to, obviously, the end of my series. So it turns out that the harmonic series diverges, but an alternating harmonic series converges. And so I'm going to explain why here. I'm going to show you in a couple of different ways. First, we're just going to look at the rule, kind of use the rule, and then we're going to look at this graphically, and it'll make a little bit more sense why what's happening is actually happening from a convergence standpoint. Okay, so this alternating series test essentially says that we have to have three things to be true. So first of all, we have to have a series that's strictly alternating. And I know in this theorem it doesn't say that, but it's making the assumption that we have an alternating series. That means that it definitely has terms that are going positive, negative, and so on. Or you can start negative, positive, so on, as long as you have alternating terms. Okay, so the next thing is your series has to be strictly decreasing. You can see that the terms are getting smaller in value, and your terms have to be approaching a value of 0. So if we're doing our nth term test as kind of a pre-check like we should be, that last part of it should already be taken care of, and then we just need to check, okay, are the terms strictly alternating? Are they strictly decreasing in value? And if those three things are true, then we know the series is going to converge. If we have a situation where the terms are getting larger, or obviously if the limit of the terms is not 0, then we can say that the series diverges. So the alternating series test can show convergence or divergence, which is kind of nice. Okay, so we have three series here, and this is actually really, really easy to do. I'm not even going to show any work on these. I'm just going to talk through these. So the first one, we've got this series, negative 1 to the n plus 1, and it's 1 over n. So this is actually the alternating harmonic series that we just looked at, written in a slightly different form. But if you plug in n as 1, you can see you get negative 1 squared, which gives me a first term that's positive. When I plug in n as 2, the second term is going to be negative, and so on. So this one actually converges, and it converges because, first of all, my series is strictly alternating. My terms are strictly decreasing in magnitude. And the last thing there is my terms are approaching a value of 0. So all of the criteria are met, so I know it's going to converge. All right, so the next one, we've got negative 1 to the n over 3 to the n. So this is actually really a geometric series, and you could see that if you grouped this together correctly, you could see that you have an r value of negative 1/3, and you could say this converges by a geometric series test. However, we can also use an alternating series test. So you can see this is strictly alternating. I can also see that the terms are going to decrease in magnitude, and I can also see that the terms are going to approach 0 as n approaches infinity. So this one converges. Now, when you use the alternating series test, I just want you to state what test you use. So you don't have to necessarily go through and show your 3 checks. If you just tell me that you're using the alternating series test, then that will be sufficient for a justification. Okay, so let's take a look at this next one. We have -1 to the n plus 1, and we've got, in terms of the magnitude of each one of these terms in this series, n plus 1 over n. You can see those terms are actually not going to approach a magnitude of 0 as n goes to infinity, so this one actually diverges. And for my justification, I could use an alternating series test. I could also use an nth term test if I really wanted to. So either way is okay in that situation. Next one here, we've got -1 to the n minus 1 over 3n minus 1. So hopefully you can see these pretty quickly now. This one converges. So I have a series that is strictly alternating. The magnitude of my terms is strictly decreasing. And in addition to that, the terms are approaching 0. And then this last one, you can see that my terms are actually approaching a magnitude of 3/4. So this one diverges. Okay, so very, very easy to use the alternating series test. So the good part is it's simple to use. The bad part is you can only use it in that one specific type of situation where you're dealing with an alternating series. Okay, so we can also talk about alternating series error. And this is also going to explain how we're seeing convergence when we have these terms that are decreasing in magnitude and approaching 0. So I can figure out the error in my series if I use a certain number of terms. So if you think back when we did the integral test and we talked about, okay, if I use the first 10 terms, how much error could I possibly have with all of the remaining terms that I have essentially left off of my sum? Well, with an alternating series test, I can easily bound the sum of my series using the size of the next term and also looking at the size of the previous term. So that's essentially what I'm going to do here, and I'll explain how this is the case. So typically we only look at this from an upper bound perspective, and the idea is if I look at the size of the next term, that tells me how far off my series approximation is from the actual sum of the series. I know it has to be less than the size of the next term. So let's talk about why that's the case. So we've got a couple of different graphs here that kind of show you what's happening. So on this one, we're looking at a series where the first term was positive. And so you can see A1 here is essentially I started at 0. And if I think about the sum of my series, I added the first term. That gets me to my first partial sum. Now, the second term is going to be negative. If this is a converging series, that second term is going to be smaller than the first term. So see how I subtracted value to get to the second partial sum? I subtracted value, but I didn't go as far to the left as I went to the right on that first term because my terms are strictly decreasing in absolute value or in magnitude. Okay, and then we're going to go a little bit to the right to get to the third partial sum, a smaller distance back to the left, and then obviously a smaller distance back to the right, and you're just going to keep going back and forth, and eventually you're going to end up with, your actual sum of your series somewhere in the middle there. So that's also why we're seeing convergence, because that same behavior is happening. What's happening when we go right and left and right and left and right and left, a lot of the value that's changing from left to right and left to right is sort of canceling out. And so we just have a very small change happening from term to term. And that change in the partial sum is approaching a value of 0. So another way you can look at it is here. We've got a couple graphs over here. If I look at the partial sums, looking at this series, you can see that my first partial sum here was positive, and then I'm going back to negative, and then I'm going back to positive, and back and forth and back and forth and back and forth. But you can see eventually my partial sums are approaching this value. This is actually converging to a value of natural log of 2. So that's a plot of the partial sums of my series. Okay, so that's the idea of kind of what's happening when I look at this. Okay, so in addition to that, you can kind of see the terms themselves. So here are the actual terms, right? If I were to look at a series where I've got the terms defined by -1 to the k plus 1 over 1 to the k. So this is the alternating harmonic series. So you can see the terms themselves are going back and forth from negative to positive, but they're approaching a value of 0. Okay, so anyway, that explains not only the error, the idea of the error, but also explains the idea of the convergence of an alternating series. So when I think about error, let's go back to the kind of main idea here. Remember I said the sum of the series was going to be somewhere in the middle here, right? Well, let's say I said I want to add up the first 4 terms. Well, I know for sure the distance I am away from the actual sum is less than the value of the next term, because the next term is going to cross back over that actual sum of the series. When I'm thinking about adding value and subtracting value and so on, whatever I'm doing with the next term is always going to take me to the right or to the left of the actual sum of the series. So all we do then, if we want to find how far off we are, we have an upper bound every time just by looking at the next term in our series. And that's really what we're going to use for our error. Okay, so for example here, let's say I wanted to deal with this alternating harmonic series. If I add up the first 5 terms, I know that I can't be off by more than whatever the next term is. So I can say that essentially my error after the first 5 terms is going to be less than 1/6. So they're referring it here to it here as the tail. Typically, we're just going to talk about maximum error, and we know it's actually less than that term. So remember, think back to this. Anytime you're trying to justify that error in your mind, you're always going back and forth across where the actual sum is. Okay, so this is where we would really use this. Determine the number of terms required to approximate the sum of the convergence series with an error of less than 0.001. Find the sum of the series with an error of less than that. Okay, so what I'm going to do here is I'm going to figure out what's the magnitude of each one of these terms. Well, here I've got that alternating, or actually I've got an alternating series here, but I've got a factorial in the denominator. So the size of each term, the magnitude of each term is just 1 over n factorial. Remember, at some point, that is going to be my error, whatever n term I need to get to. So I need that to be less than 0.001. So when you solve this out, this is actually something we're just going to do on the calculator. And I'll go through this a little bit in class just to clarify. But the main thing is I can just enter 1 over n factorial as a function, and then I can look at the table in the calculator and figure out, okay, at what n value am I smaller than 0.001? It turns out for this one, I get the 7th term, n equals 7, gives me a number that is less than 0.001. So that means I need to add 6 terms. So the sum of my series from 1 to infinity would be from 1 to 6 is going to be my approximation for this series. And then I can just do -1 to the n plus 1 over n factorial. And I would just plug that into the calculator. And whatever the calculator gives me for the sum of those first 6 terms, that's my approximation for the sum of the series. I know that that's not the actual sum, but I also know that I am off by less than 0.001 because the 7th term in that series has a value of less than 0.001. So that's essentially how it works. Okay, so same idea on the next one. We would do the same process here. You can see that this is an alternating series that converges, and I would look at the magnitude of the terms, 1 over 2 to the n factorial. Again, I would enter that as like my y1 on my calculator, pull up the table of values and figure out, okay, at what point am I less than 0.001 in terms of value here? And that would happen when n is equal to 5. So that's true at n is 5. That means I need to add up the first 4 terms. So I just go up here and I can approximate this by n is 1 to 4. And let me fix my 4 there. That would be just this plugged into the calculator, -1 to the n over 2 to the n factorial. And again, plug that into the calculator, and that would give you an approximation for the sum of the series. And we know we're accurate at least out to or within 1/1000th. So that's really the idea behind it. It's very, very easy to do, but it does require you to use the calculator because you're going to get obviously these decimals that you have to deal with. That these are not things you're going to work out by hand. Okay, so be careful when they ask you questions about accuracy to a certain decimal place. So when they ask you for accuracy to a certain decimal place, we have to take rounding into account. So for example, if we want accuracy to the first decimal place, we have to go and say our error needs to be less than 0.05 because we're taking into account, that could make my one decimal place round up or down. And so if we make sure we're within 0.05, then we know that our rounding has been accounted for. So you can see here, 2 decimal place accuracy would be 0.005. So be careful with the wording on the question. Sometimes they'll tell you specifically, like on this one, be accurate to within 1/1000th. Sometimes they'll say accuracy to a certain decimal place. And depending on how they word it, you have a slightly different setup in that error calculation. All right, so the last thing here is absolute convergence. And the idea of absolute convergence is that if I can show that a series converges with the absolute value of all of the terms, then the series has to converge in its other form. And so this is something that we use a lot when we're talking about the ratio test. If you remember when we were doing the ratio test the last time, I said I wanted to set it up with an absolute value because this is actually how we're going to use it. We're going to use it to get the interval of convergence for a series. And so the idea is with a ratio test, I can show absolute convergence. With a root test, I can show absolute convergence. And then I also have this test that I can use kind of independently of that. So it says determine whether the series is absolutely convergent, conditionally convergent, or divergent. So I'm going to explain what that means. So if I've got a series that looks like this, -1 to the n plus 1 over square root of n, I want to look at it in different forms. So to start with here, in its alternating form, in the form that it's in, this converges, right? Okay, so what I also want to look at is what happens if I were to look at it in this form and take the absolute value of -1 to the n plus 1 over square root of n. Well, what that turns into is just n equals 1 to infinity, 1 over square root of n, right? And we know that that actually diverges. So notice that in the form I was given, it converged, but in its absolute form, it diverged. So when we have this situation, this is referred to as conditionally convergent. So in order for it to be absolutely convergent, it's going to have to converge in its absolute form. So basically making all of the terms positive. Okay, so here's another example of that. You can see on this one, I'm not even going to check from the other perspective first, because if I check absolute convergence or the absolute form of this series and I show absolute convergence, I know it's going to converge in all its forms. So what I'm going to do here is I'm going to look at this series from 2 to infinity. I'm going to take the absolute value of this, -1 to the n over n cubed minus 1. And that's the same as now having this series from n is 2 to infinity, n over n cubed minus 1. Now remember when we were doing all that stuff with limit comparison and I said there's going to be situations where we want to be able to do these in our head? This is a good situation. I don't want to show all the steps here, but I do want to know that this series converges by a limit comparison to a 1 over n squared. So I know this converges, right? Well, we're looking at absolute convergence. So since we're looking at absolute convergence, I just lost my... Okay, so since we're looking at absolute convergence, the idea that this series converged in its absolute form, that means that it's also going to converge in its alternating form. Okay, so we can say this converges absolutely or it has absolute convergence.
Hello.
Hey. I'm making a video right now, so I'm just gonna finish it because I've got like 2 minutes left. All right, so we have a couple more here. This one's an alternating series again. If we look at it in its alternating form, you can see it diverges. But also, if we were to look at it in its absolute form, so I'm going to put all of this, and essentially this is just now not an alternating series. you can see that that is still in a form where it's going to diverge, because by the nth term test, I can see that it's got divergence. So the terms are not approaching zero. So for this one, it diverges in every form. It diverges in its alternating form, and it diverges in the absolute form. So we would say this one is just divergent or diverges absolutely. All right, and then the last one here, this is really where we have the most kind of powerful use of this type of convergence. So we have cosine n over n squared. If we were to go through and plug in n values, you would see that this is a series that has terms that are positive and negative, but it's not actually an alternating series. It doesn't strictly alternate from positive to negative every time. But even though it doesn't do that, I can still show convergence for this series. So this is one where, you know, all of my tests don't really work for me. I don't have a good way that I can look at a series that has like positive, positive, negative, you know, negative, positive, 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 negative, negative. So not really a pattern to it. So what I'll do instead then is I'll look at this and I'll say, okay, let's just check for absolute convergence. From 1 to infinity, we've got cosine n over n squared. Well, if I make cosine n absolute, that means it's always going to be positive. So I can actually do a direct comparison here. This is going to be less than the series from n is 1 to infinity of 1 over n squared, because I know for sure that cosine, the biggest it can ever get is 1. Most of the time it's going to be less than 1. So if I were to put these terms side by side, in general, the terms for cosine n over n squared are going to be smaller than 1 over n squared. Well, 1 over n squared converges. So that means that my series for absolute value of cosine n over n squared is also going to converge. So this is absolutely convergent. So that means this series, this original series, converges. Okay, so that's really where we're going to use absolute convergence the most, is in kind of special case situations like that. It can really help us find convergence for a series that doesn't fall into any of the categories that work for all of the 10 tests that we have. Okay, so as you go through this assignment, just keep in mind you're going to start seeing these tests all mixed together. So it's not just understanding the alternating series test and the absolute convergence. It's also going to be keeping those other ones in your mind as you work through the problems. You're going to need to know all of those different tests.